We'll begin today with number 17. Um, we were given the free energies of formation of liquid water at minus 237.1 kilojoules and the delta H of formation of gaseous water at minus 228.6 kilojoules. We're asked to calculate the equilibrium vapor pressure of water at 25 degrees, and we're given the ideal gas constant R at 8.314 joules per mole per Kelvin, and 1 atmosphere is 760 torr. So let's set this up and we'll begin to work number 17. I need another pen. New. Number 17. And we're to get the equilibrium constant from free energy values. So what we should remember is that delta G superscript is equal to minus RT ln of Kp. Now the reaction that we have is H2O liquid in equilibrium with H2O gaseous. And if I'm looking at the equilibrium constant for this type of heterogeneous equilibrium, Kp is just going to be the partial pressure of the water divided by 1. Liquid water is not in the phase with gaseous water. So the equilibrium constant for this reaction is just the vapor pressure of water. So this will allow us to do the calculation. So the delta G superscript for this reaction is going to be the delta G of formation of gaseous water, and delta G of formation of gaseous water is minus 228.6 kilojoules, and we have to subtract from that the delta G of formation of liquid water, and that's a minus 237.1 kilojoules. So this term's going to be positive, that one negative, so I'm going to take 237.1, and subtract 228.6, and I get 8.5 kilojoules. So the delta G for the reaction is plus 8.5 times 10 to the third joules. I wrote it that way because we have to now set this equal to minus 8.314 joules per mole per Kelvin times the temperature would be 25 is 298.15, and then times the log of the vapor pressure of the water. All right, so the log of the vapor pressure of the water is going to be equal to 8.5 times 10 to the third divided by 8.31 minus 8.314 and 298.15. We can do that math. Let's see what we come up with. So 8.5 with an exponent of 3 divided by minus 8.314 and divide by 298.15, I come up with the ln of Kp, or P in this case, is just going to be minus 3.429 and some other digits. So the pressure, P, is going to be E to the minus 3.429. And what do we come up with? If I take second E to that answer, I get the vapor pressure is 0.032417 and some other digits. So now this is in atmospheres. So the pressure, if I convert that, 0.0324 and the other digits, and this is atmospheres. And there, in one atmosphere, there's 760 torr. So I need to multiply that times 760. And I get 24.63. P is going to be equal to 24.63 torr. So if we go back then and take a look at our answer, I think this is the correct answer. Yes, 24.6 torr. Now, let's look at number 18. Now, number 18 says, give the abbreviated cell notation for a cell containing a salt bridge separating silver metal from 1 molar silver ion in one compartment and another containing mercury metal and mercury +2 ion concentration of 1 molar if the cell delivers a positive voltage. So I'm going to look at the data page here. Let's see. And I'm going to write them both in reduction now. We've got Hg 2 plus and Hg. That's one reduction. The other one is Ag plus reduced to Ag metal. And now let's go to the data table and get the values. Here are the cell potentials, and we're looking for silver and mercury. They're fairly low on the table, right adjacent to each other, right here. So the Ag plus reduction occurs at plus 0.84 volts, and the mercury reduction is plus 0.85 volts. Okay, I've got the data that I need. Now let's switch over. Go back to where we were, number 18. And then look at our pad. We've got the data set up. We had mercury in reduction is at plus 0.85 volts. Silver in reduction is plus 0.84. So I've got to turn one of these around. If I want to keep a positive voltage, it did say when it's spontaneous, and voltage has to be positive to be spontaneous. So what I want to do is I want to take this one and subtract this one. So the reduction potential will be the mercury. So it's going to be an Hg plus 2 Hg. And reduction is supposed to be on the right of my cell, so I should have thought ahead. Reduction's on the right, so oxidation is going to be the left. So I'm going to go to Ag to Ag plus on the oxidation cell. So the reduction is on the right and oxidation would be on the left. So this is what we're looking for in the answer. And if I want to write down the E0 for that, we had plus 85 minus 84 gives us plus 0.01. So that'll be the voltage of that cell when it actually is delivering current at standard concentrations. Let's go take a look at our screen again and see that that's what we have. Yes, the correct answer is B. Silver is in oxidation. See, silver's going to +1. That's oxidation. Mercury's going from +2 to 0. That's reduction. And so that would give us the voltage for this cell. Now, number 19 is going to be related to that. So let's see if we can set that up. We want to get the cell voltage at other than 1 molar concentrations. So that's going to be the Nernst equation. Let's go over to the notepad. We probably have enough room to do it. E is going to be equal to E0 minus 0.0591 over N. Now, this is a 1 electron change. This is a 2 electron change. So I would have to multiply this cell through by 2 in order to have electrons gained and lost be the same. So the number of electrons that would cancel out of the 2 half reactions would be 2. So this is a 2 here. 0.0591 over N log of Q. Now Q, we have to write the reaction out in order to tell how this is going. So one of our half reactions is this one. It's in oxidation. So this is a reactant, and this is the product. The other reactant is this. So what we're going to do is we're going to have Ag plus Hg 2 plus going to Ag plus Hg. And of course, mercury's a liquid. I've not put the phases into the others. But my coefficient now, I have to have 2 of these to balance the charge on both sides. So I've got a +2 charge on this side. Now I've got a +2 charge on that side. So again, that's why we put the 2 in here. I wanted to write out the reaction so you could see that the silver ion is the product. And so the Q is going to be the product concentration of silver. So this is going to be, I'll just write it up here and then we'll put the numbers in below. Ag plus concentration. And the balancing coefficient is 2, so that's squared, divided by the mercury concentration, Hg plus 2, and that coefficient is a 1, so it's just to the first power. So let's put in the numbers that we have now. So we have 0.01 is the E0 minus 0.0591 divided by 2, log, the silver plus concentration given in this problem is 1.6 molar. And that is squared. And the mercury concentration given in the problem is 0.01. And of course, that's to the first power. So let's do this math. So I'm going to take 1.6 squared, and divide that by 0.01. This gives me 256. I'm going to take the log of that answer. I'm going to multiply that by minus 0.0591 and divide it by 2. And that gives me minus 0.07. And now I'm going to add to that 0.01. So plus 0.01. So my overall cell voltage now at this set of concentrations, now it's not the E0 anymore, it's minus 0.06. And I guess I could have a 1, 2, I'd say. Okay, so, okay, dokie. seeing a problem. Okay, let's check my math again. See if the concentrations are what I had here. Okay, yeah, it's still, okay. So the cell voltage, I'm sure we did, the standard voltage, I'm sure we did that right. If I copied, I'm pretty sure I copied the two numbers correctly. So let's go back up here and double check. Okay, the silver ion the silver electrode reduction potential. Oh, no, we didn't do it right. I copied it wrong a while ago. So that's going to start all over again. All right, let's get a new piece of paper and just redo it because I copied the cell voltages down there the first time. Okay, so we're doing number 19. And the Ag plus reduction, the Ag plus reduction to Ag, that occurs at plus 0.80 volts. The Hg plus 2 to Hg reduction, that occurs at plus 0.85. Okay, so now if I want this one in reduction, so I did have it set up correctly. The Ag needs to be in oxidation, so Ag to Ag plus, that's oxidation. And this voltage then would be minus 0.80. And this mercury in reduction, Hg plus 2 to Hg, that's at plus 0.85 volts. And the zero of the cell is going to be plus 0.05 volts. And that's why we missed the other problem. We had 0.01 here. So I don't know where I got that number from that table of data. All right, so let's go back to number 19 and look at it again. Now, so the E0 of the cell, and we wrote the reaction was Hg, it was Ag plus Hg2 plus goes to Ag plus Hg, and we do need 2 silvers to do that. So, and the mercury concentration given on the problem was 0.01 molar. The silver ion concentration given on the problem is 1.6 molar. Okay, I can give you a little bit bigger view of the, no, that's good. Let's just continue the way we are. We're doing fine. And the E then is going to be the E0 minus 0.0591 over N log of the Ag plus concentration squared divided by the Hg plus 2 concentration. All right, so the E0 was plus 0.05 volts minus 0.0591 over 2 LOG of 1.6 squared divided by 0.01 to the first power. All right, now let's try that again. So I get 1.6 squared divided by 0.01. And that's 256 again. Log of that answer is 2.40 times minus 0.0591 divide by 2, and then plus 0.05. And I get the E of this cell is minus 0.02116 volts. And I think that's okay. There we go. And minus 0.021 is correct. And now it says calculate the concentration quotient for a cell having a salt bridge, separated silver and silver ion, whatever, from the other compartment. When this cell runs down, and I see two ends in run, so that really catching a typo here. And let's save that so it'll be fixed next time. Okay, so we want, this is number 20. And what we want to do is now calculate the concentration quotient for the cell containing the salt bridge with silver ion at 1 molar and mercury ion at 1 molar when it runs down. So what the voltage, we still use the Nernst equation up here. So rather than recopy it, I'll just go up here, and I'm looking at this, and I want the voltage to be 0. So 0 has to equal to the E0 minus 0.0591 over 2 LOG of Q. We want to know what that concentration quotient will be when this stops delivering a current. Okay, so 0 is going to be the E0 of the cell. We calculated up here was plus 0.05 volts minus 0.0591 over 2 LOG of Q. I'll bring this term across, and that gives me plus 0.0591 over 2 LOG of Q is equal to 0.05. All right, so the LOG of Q is going to be 2 cross multiply 2 times 0.05 divided by 0.0591. And we can do that math. 2 times 0.05 divided by 0.0591 is the LOG of Q is going to be 1.692. Okay, and Q is going to be 10 to that power. Second, 10 to the second. Answer is 49.2. Oh, 49. Yes, I got 49.2. That's, I see a little bit of a difference, but it's still within the range that we said it would be. 49 point, the 3 significant figures is what I really should have. that would be 49.1. And I got 49.2 when I worked it out. So that's close enough to identify that as the correct answer. Okay. All right, moving right along. Number 21. Calculate the standard voltage E0 of a spontaneous electrochemical cell shown on the data page. So let's go up to the data page and look at it. And what we want for number 22 is we want the E of the cell, not the E0. So let's go up and look at the figure on this data page. There it is right there. It is the same cell that we're looking at, that we've been doing calculations on, except the concentrations are different. I've got silver and a silver ion cell, and I've got mercury in a mercury +2 cell. Remember, mercury is a liquid. It's a liquid metal, so that's why we're making the contact the way we are. The surface of the liquid metal is inside the beaker here with the mercury +2 ion in it. So again, what we want to do is we want to do a standard reduction potential, and we calculated a while ago. I've got that reaction written down 2 or 3 times. Our reaction that generated the positive voltage was 2Ag plus Hg2 plus goes to 2Ag plus Hg2 plus. Wait, no, it's 2Ag plus. Okay, all right. And we got the E0 for that cell was plus 0.05. All right, so, and the silver ion concentration in the cell is 2.15 molar. And the Hg+2 concentration is 0.0019 molar. Okay, I've got everything I need, so let's go over to the pad. So our reaction is 2 silvers and a mercury +2 goes to 2 silver ions plus a mercury +2. Concentration of the mercury is 0.0019, and the concentration of the silver is 2.15. So E is E0 minus 0.0591 over 2. LOG of the silver ion concentration is 0.0019, and that's squared. And the silver ion concentration is, I'm sorry, I got that backwards. I've got to read off the book. The mercury is 0.00, look at my cell reaction again. Silver was oxidized to +2, and mercury, this is the +2 here. This is just mercury liquid on this side over here. Yeah, copied the reaction wrong a little bit. Okay, so let's redo that. E is E0 is plus 0.05 minus 0.0591 over 2. LOG of the silver ion concentration, right? Yes, the silver ion concentration is 2.15. and that is squared, divided by the mercury concentration is 0.0019. And that's to the first power. Okay, so let's do the math. I get 2.15 squared divided by 0.0019. Okay, and that's a little over 2,000. The log of that answer is 3.386 times minus 0.0591 divided by 2 is about minus 0.1 plus 0.05. So the E for this cell is going to be equal to minus 0.05 volts. Well, how cute is that? We went from plus 0.05 to minus 0.05. So let's go back. Looks like a kind of cute little problem I would dream up. All right. Okay, so okay, the voltage for the cell is at minus 0.05 volts, and if I need to share that screen with you, and then you can see we were successful. We got the standard voltage is 0.05, and we got the cell voltage at those concentrations at minus 0.05. So those two answers are both correct. Now 23, calculate the equilibrium constant for the spontaneous electrochemical cell shown on the data page. Now, remember that the spontaneous electrochemical cell would have to have a positive voltage. So the voltage that we're going to use in number 23 the A0 is plus 0.05 volts. Okay, so let's get the pad up here where we can see it again. All right, so the voltage there, and what we're asked to calculate is the equilibrium constant. Well, E0 delta G superscript is equal to minus N F E0. And delta G superscript is minus RT ln of K. So this, if I put these two together, a minus N F E0 is minus RT ln of K. Minuses would cancel from both sides. So divide through by RT, I get the ln of K is equal to NF E0 over RT, where F is the Faraday constant and F is 96,500 coulombs. So my ln of K is the number of electrons transferred in that reaction was 2. 2 gained and 2 lost, times 96,500. The voltage was plus 0.05 divided by R. R has to be the 8.314 value. And the temperature is 298.15. So there's all the bunch of numbers that we have to then do the calculation. So we get 2 times 96,500 times 0.05 divided by 8.314 and divided by 298.15. So I'm getting the ln of K to equal 3.892, and K would be equal e to that power. Is 49.0569 and a bunch of digits. So let's take a look and see if that's what we got for an answer over here. So I can go here and look at this. And sure enough, 49.1 is the correct answer. Now, using the concentration shown on the figure for the electrochemical cell on the data page, we're trying to determine the direction of electron flow and other things in the circuit. So now, hang on with me just a second here, because we've got things to remember. Now, we're talking about this cell right here. And when we wrote that cell, again, remember the reaction was 2Ag plus, Hg 2 plus goes to 2Ag plus Hg. Now, that's the reaction that's taking place. But when we put in the concentrations that was on this cell, I guess I should go on and write them in. This was at 2.15 molar, and the mercury concentration was 0.0019. Okay, so let's go back and share, because I'll come back to this screen, but I want you to see the pad again. So at this set of concentrations, the E for this cell was minus 0.05. So that's going to tell me that the reaction is actually the other direction. So I need to turn the reaction around to make that a positive voltage. Now, why do I do that? Because nature don't know that I decided that if it's going in this direction, for example, silver is going to silver +1. The electrons that are lost don't go in the solution. They go on the silver wire. So that would make the silver wire the negative electrode, and electrons would be traveling from it to the other side in the salt bridge. But since the voltage is negative, the reverse is true. In the cell that we're talking about, the electrons now are produced on the platinum wire that goes to the mercury metal down here. So this is going to be the negative electrode. Negative electrons are going to flow through the external circuit from right to left. Negative charge is going to go through the salt bridge to complete the circuit. So if I'm looking at the top of the salt bridge here, negative ions are traveling to the right to get into this. And then more negative electrons, and then more negative ions here. So the way this is flowing is the platinum electrode is negative, and the anions are moving from left to right in the salt bridge. Let's see, what did it ask me to do in number 24? I'm going to look at that again. Okay, electrons flow from the platinum to the silver. Number 1 is true. Potassium ions in the salt bridge move into the silver ion side. Well, if the anions are moving from the silver into the mercury side, the potassium ions, the positive ions, are moving in the opposite direction. So both statements are true. And that's the correct answer if we look at the look over here. You can see both statements are true is marked as the correct answer. So the electrons do flow from the platinum wire to the silver, and the cations are going to move into that silver compartment too, in order for that to remain charge neutral. Okay. All right. So be careful in a question like that, because especially if it's sort of straightforward if the voltage of the cell is positive. But if the voltage you calculate for the cell is negative, you've got to remember to reverse the direction that you set up when you used a Nernst equation to calculate the voltage. Okay. And that's kind of a tough statement, but okay. Now, using the concentration shown in the figure, an electrochemical cell on the data page, the silver electrode, oh my goodness, I see another, it's electrode, not electros, electrode. Okay, save it. All right, the silver electrode is positive, and the silver electrode is an anode. Okay, well, let's go back now and look at what's really taking place. And this time, I'm going to go ahead and write the reaction in the direction that created the positive voltage. So let's stop the screen share so you can see my padding down here again. Now, this is the reaction here that generates the negative voltage. So I want to turn it around. I'm going to go Hg plus 2Ag plus, and again at that concentration, 2.15 molar, whatever that was. I'll read over there when I get there. It's going to go to 2Ag plus Hg 2 plus, and this is at 0.0019. And the E for this cell is now plus 0.05 volts at this set of concentrations. Okay, now let's look at what's happening. I always look at the oxidation that takes place. Here's the oxidation that takes place. So that means the mercury is going to mercury plus 2. The 2 electrons are going to travel from the mercury electrode. In this case, it's going to be platinum, over toward the silver ion. So this electrode is going to be the negative electrode. It is oxidation, and that's the anode. And then, of course, the other electrode is reduction, and cathode. So let's see what the, okay, we're looking at number 25. And it says the silver electrode is positive. Well, if the mercury one is negative, the silver one is positive. So that should be true. Now, the silver electrode is the anode. Well, no, I said mercury was oxidized, so mercury is the anode. So statement number 2 is false. So number 1 is true and number 2 is false. Let's look at our screen share and see if that's correct. Yes, only statement 1 is true. Okay, for number 6. Using the concentrations shown in the figure for the electrochemical cell on the data page, which of the following is true? So now I have the electrode written the way it's supposed to be when this is actually happening. Remember, if it's negative, it's not happening like that, but it is happening in the other direction. So I wrote it in a direction that would give me a positive voltage, and that allows me to make all of these judgments. So let's come back over to our pad again. And so you see, this now is the reaction that is going to take place. And it says adding water to the silver compartment would increase the voltage. Okay, here's the silver compartment. Silver is a reactant. Silver ion is a reactant. If I add water, I dilute this. So the concentration of the Ag plus concentration goes down. Now, by Le Chatelier's principle, if I decrease this concentration, what does equilibrium do? It shifts left to make more of that silver ion. So shifting left, it decreases the voltage. So adding water decreases this concentration and causes the voltage also to go down because I've decreased the reactant concentration. Equilibrium shifts to the left. So adding water to the silver compartment increases the voltage. Statement 1 is false. Okay, statement 2. Adding water to the mercury compartment increases the voltage. Well, here's mercury here. Mercury ion is a product. So Hg plus 2 is a product. So if I decrease the adding water, is going to decrease the mercury plus 2 concentration. That's going to go down. Now, equilibrium shifts to toward that product I've reduced. It's going to shift to the right. That's going to increase the voltage. So the voltage is going to go up. So number 1 is false, but number 2 is true. So, and I think that is what the one that was marked is correct over here. Only statement 2 is true. Okay. Now, using the concentration shown on the figure for the electrochemical cell on the data page, which of these statements is or are true? We're going to add silver nitrate to the silver compartment. So 27, I'm going to, first of all, I want to notice silver is a reactant. Is a reactant. And if silver ion is a reactant, I'm going to add silver nitrate, which is a soluble silver salt. So that's going to cause the Ag plus concentration, a reactant, to go up. By the Shockley A, it shifts right. That causes the voltage also to go up. Okay, so get back over my pad so you can kind of watch it as I'm doing this. All right, now the second statement, so statement number 1 said adding silver nitrate increases the voltage. It's true. All right, it says adding mercury nitrate to the mercury compartment. So let's look at the Hg plus 2. Notice Hg plus 2 is a product. And I'm going to add mercury nitrate, mercury 1 nitrate to it. That's going to increase, it's mercury 2 nitrate. That's going to increase the product concentration. So Hg plus 2 concentration is going up. It's a product, which means equilibrium shifts away from that toward the other side, which means that the voltage goes down. So number 2 is false. And if we go back to look at our screen share, that is the correct answer. So we were able to do the reasoning for this. I guess the thing I would really caution you about carefully is when you make these kinds of judgments, be sure that if the voltage that you calculated using the standard voltages and the standard concentrations for the spontaneous cell, we're going to use that always as reference. The reaction we think occurs at standard concentrations is the one that would give us a positive voltage. If we calculate the voltage at some other set of concentrations other than 1 mole per liter of all the soluble things, 1 atmospheric pressure for hydrogen, for example, if we've got concentrations other than those values, we calculate the voltage then. If that new voltage is still positive, the reaction that we're considering is still going in the direction we wrote down when we wrote the spontaneous cell from the standard reduction potentials. But if that voltage turns out negative, the reverse reaction is the one that occurs. And please write that down. Turn the other one around and write down the one that actually does take place before you answer questions like the last 3 or 4 that we saw here. Otherwise, you will get just the opposite answers. And as you noticed in all of these statements, those answers are here. So be very, very careful when you're working with voltages that come out to be negative. We're always going to go to our standard tables. We're always going to write down the direction that would give us a positive voltage at 1 molar concentrations. But if the voltage is not positive, write the reaction down reversed, and then answer the rest of the questions, because it changes everything. It changes which electrode is positive and which one's negative. It changes which electrode is the anode and which one's the cathode. It changes the direction of the electron flow in the wire. It changes the direction of the ion flow inside the salt bridge. So all of those answers will be wrong if you didn't take that sign into account. Okay, all right. That's enough. That finishes the practice quiz. I hope this helps you, and I will end the recording now, and I will upload it to D2L as soon as it's processed.